Okay, here we are. It's the physics video lecture once again. That's physics 107B video lecture 25. And we're talking about relativistic mechanics. So I'm going to write down a bunch of the stuff we had last time just to list it all. And so relativistic mechanics. And then we want to solve a couple of interesting problems. Okay, we started with the Lagrangian formalism, but I tried to motivate primarily by relating it to the proper time and then taking the small velocity limit. This is the Lagrangian of a free particle right here, and the small velocity limit turns into half mv squared. Okay. Now this I did not motivate, but I'm just going to put it there for the record. A dot v minus q times potential v, maybe I should call it phi. We've actually seen this before in mechanics for the motion of a charged particle, and this is actually the relativistic Lagrangian for a charged particle in electric and magnetic fields. So you have to take the gradient to get the electric, you have to take the curl of A to get the magnetic field. Good. So I'll even circle in red what we actually worked with. Likewise, we found energy mc squared over root 1 minus v squared over c squared. Very important expression. For the full expression, that would be your energy. And this follows, I'll just write here, from energy equals dl dv dot v minus L. So actually if you do this operation, right, this is what we know from Lagrangian mechanics. On this Lagrangian, you'll get this energy here. And again, for the free particle, we were just working with that right there. And this actually came from this dl dv vector, which was P equals mv over root 1 minus v squared over c squared. So yeah, here's what I'll do. And then I'll repeat this. Energy equals mc squared 1 minus v squared over c squared. So this version is for the free particle, and we'll have something to say about that. There's some subtleties involved. The Hamiltonian is the energy in which we've replaced v squared with this v squared here, solved for p. So this energy here, m squared c to the fourth plus c squared p squared, is the Hamiltonian. In other words, this is exactly the same value of energy, but it's in the form in terms of the momentum instead of the velocity. Okay. Yeah, we're going to make use of that. And then there was one more thing, namely, if we take this energy and divide by c squared and multiply by v, we get p. So we have energy over c squared, that's that m over this times v is equal to p. So these are all for a free particle. And what we want to do is integrate this for a constant force. So this actually, these were for the free particle. This is actually just the definition of the momentum. Okay. So maybe I should strike that and say these here. Free particle. That means force-free particle. We're actually going to use this to integrate the differential equation. So yeah, we see that property here. We're apparently forbidden to reach the speed of light, okay, because then, or to exceed the speed of light in particular. Right, we saw that we can reach the speed of light if we have a massless particle, then the speed is the speed of light. But for a massive particle, we're not going to be able to reach the speed of light. So we want to do an integration of this differential equation and actually see what happens. So the force law that goes with that Lagrangian, for instance, is going to be dp dt is equal to q times E plus qv cross B. And our first case, we're going to consider motion, say, in the x direction, and we're going to have, I'll just write motion along x, and we're going to have with f equals qe. So we're just considering motion in the x direction. And now we can take this equation of motion and say we have dp dt is equal to qe, okay? And E is, constant. So uniform field constant force. So what we're going to be integrating is, since this is constant, we have P is equal to QET plus P0. Here we're going to strike that and just have, there we go. We've integrated the differential equation. Momentum is equal to Q times E times T. But of course, the momentum is also equal to mv over this here. And we have mv, so we're just in one dimension, one direction. mv over root 1 minus v squared over c squared is equal to qet. And I'm going to abbreviate that. Anyway, let's go ahead and, so now what we have to do is find v of t. So we can see it's really just an algebraic problem. Find v of t. Okay, well, we're going to clear this up. So for this, we just have to do a little bit of algebra. First of all, we're going to write v over c over root 1 minus v squared over c squared is equal to qet divided by mc. And q times e is f, that's fine. So qet over mc. And in fact, I'm going to call this a times t And then we'll have v squared over c squared is equal to 1 minus v squared over c squared times this a times t. V squared over c squared times 1 plus a times t is equal to a times t. So v of t, when the dust settles, we have c, and we'll actually just retain that letter a for the time being. A times t over 1 plus a t. Did I forget to square something? Yeah, squared a t squared. A t squared like that. Is that right? Yeah. Yeah, squared both sides. So a t squared. Took the square root. Good. So yeah, let's look at this. We know that A is just equal to this QET over MC, so we don't have to plug that in anymore. What we want to note is, note the limit as t goes to infinity. And the limit as t goes to infinity, we got AT over AT, right? Take the square root. That cancels and we just have C. So limit t goes to infinity, v of t is equal to the speed of light. It never exceeds the speed of light, and you have to take t out to infinity to get that. Good, so there's that. Let's also integrate this now. So next, we're going to have x minus x naught is equal to the integral v of t prime dt prime. And when we integrate this, we're going to have square root plus at squared from 0 to t. So yeah, let's see. 1/2 to a squared t. One of the a's cancels. So that is c over a root 1 plus at squared minus 1. And let's inspect that as well. I'll go ahead and erase this. So x equals x0 plus c over a root 1 plus at squared minus 1. So again, we're looking at the limiting behavior. So in the limiting behavior, in keeping with this limiting speed here, as t goes to infinity, you're going to pull out, you're going to neglect the 1, you can have a, cancel that, square root of t squared is t, you're just going to have x naught plus c times t, so it's got that linear growth as time goes to infinity. So check, t goes to infinity, x goes to just c times t, plus whatever constant. Now, at much less than 1 is also a good one to check. Then we will have x equals x0 plus, we've got the c over a, and now at is going to be small, so we'll take 1 plus 1/2 of this at, the quantity squared. That's our approximation for the root 1 plus something small minus the 1. That goes away. We get x0 plus, one of the a's cancels, so we have plus c a t squared over 2. And that a was equal to QE over MC. C cancels T squared. So that's force over mass. So 1/2 force over mass T squared, 1/2 acceleration T squared. So at short times, it's just doing the standard distance square time squared law, but at long times it asymptotically approaches the speed of light. Okay, so that result is good. Now the next one we want to do is going to be trickier. We want to have the motion in x and y, because we're going to get the relativistic version of what we could call projectile motion. So let's send this up. And rewrite everything. Okay, so next, again, it's going to be dP dt is equal to QE. E is going to be equal to a constant. I'm going to have this time, I'm going to have E is equal to E I hat. So there's no field in the y direction. There's this field in the x direction. But nonetheless, this is just as easy to integrate as before. So dpx dt is equal to QE. dpy dt is equal to 0. So we'll have piece of x, just what we had before, QET plus px0, py is going to be equal to py0. Okay. And for our problem, we're going to go ahead and set this one equal to 0, and then we'll relabel these things by and by. Okay. But first we have to set up our differential equation. Okay, so the relativistic momentum is a vector, and we already solved for the momentum, so we have mvx over root 1 minus v squared over c squared. That's the piece of x is equal to QET, and then the m v sub y is simply equal to the p sub y 0, which is a constant. Now here's the problem. these v squareds, top and bottom here, are equal to v squared equals vx squared plus vy squared. So these equations are coupled in a way that would be very difficult to solve. In fact, I'm not sure how I would solve it if I use these. There's a way around this problem though. And the way around that is to use so equations are coupled, so difficult, very difficult to solve. I'll just write problem, exclamation point. Let's see. But we had this expression E over C squared V was equal to P. Now this was for a free particle, so we're going to have to be careful in the interpretation, but this will lead to a good solution. And this H, so we're going to use these free particle results, m squared c to the fourth, c squared p squared. The key to this is going to be that we already have p explicitly, as functions of time. So what we're going to do is evaluate this thing here. So the Vx, we have the dx dt is equal to c squared over energy times the p sub x, right? That's v sub x dx dt, and the p sub x is this, QET. E field T. And we have the dy dt is equal to the c squared of this E, and that's just py sub 0, py 0. And this energy here, okay, this is from the Hamiltonian. So I can write this as m squared c to the fourth plus c squared. Now the p squared, that's just the square, so that's px squared plus py squared. So that's plus c squared p0y squared plus c squared QET squared. Okay. So this is the key to solving the problem, those otherwise impossibly coupled equations. And this needs a little bit of discussion before we go on. Because again, this was the Hamiltonian for the free particle. But what we have now is we're not treating it as a Hamiltonian, it's just a value of the energy, okay? Then we said it's the energy of the free particle. But since we have explicit time dependence already here, this is simply the energy of a particle at a given time, okay? So that's why we can use this. This is simply an expression for the relativistic energy of this particle at time t. And because it's explicitly a function of time, when we put it in here, we will have two expressions, explicitly functions of time, that we can just integrate up. Okay, so that, you may want to write down a little bit of commentary that I just said there, how we're justifying using something that we said was for a free particle. This is not a free particle. Okay, it's under a constant force. So in essence, we're just treating this as a kinematic problem at this point. Good. It's a kinematic problem. I'll say again, the dynamics was the solution for P, right? We solved this explicitly, and what's left is a kinematic problem because the value of the P that we have explicitly is also in there, and so now the dV, the dx dt and dy dt have to now be solved. So let's go ahead and write that out. There are a number of constants involved, but a lot of letters, but otherwise it's similar to what we just did. Let's see here. Yeah, just to make sure we write this out. We'll do the x integration first. Okay, so we have x integrating x equals x0 plus, I'm just going to write these out, c integral c q e t prime dt prime. This is 0 to t, and the denominator is this thing here, function of time, m squared c to the fourth plus p0 squared c squared, and then the c q e t, the entire thing squared. And you can see this is nice. We've got this here and this right there. So it's the same integral we did before, except it's just garnished with more numbers. And I'm going to, well, yeah, I'll put it up here. Here's what I'm going to do. So 1 over QE root m squared c to the fourth c squared p0 squared. You see I dropped the subscript on the p supply. I'm just going to call it p0 plus c q e t squared. So what I've done is I've dropped the constants here. Those are constants, x0 plus the lower bound of this expression. That's a constant. We'll drop it and we'll just retain this right here. That's sufficient. It's really the same problem we had before. Okay, so in terms of x, we have the same thing, except this is more complicated. We've got that rest energy squared plus this from the constant linear momentum component squared as well. So I'll just write here simplifies to this thing here, and we can do the same analysis we did before, namely, well, actually, without these constants, the small time analysis we can't actually do, but doesn't matter. We did it already. The long time analysis, this thing runs away, right? This part diverges here. So what this goes to for t goes to infinity is c q e t over QE, C times T. So just as we had before. Good. So what about the y? So this is x of t. Go ahead and write x of t. X of t y0 plus integral 0 to t dt prime. And then we have to use this expression here. So c squared p, well, I'm calling it p0 now. Okay. Let p0 equal py0. And this expression here. So this one we have to recognize or look up in an integral table. So c squared p0 squared plus c qet quantity squared square root. So when you do some substitutions, or the other way around, if you do some substitutions, you end up with an integral dt over root 1 plus t squared. Okay? That's the basic integral that you're looking at here, okay? The dt and the t to the t prime. And that is the inverse hyperbolic sine of t. Okay. So this integral is going to be the inverse hyperbolic sine, and you can do that in a couple of steps. You know, you can pull this out, divide top and bottom. I'll do a couple steps. So we would have y0 plus c squared p0. We'll pull out this root m squared c to the fourth plus c squared p0 squared. And yeah, then we'd have our dt root 1 plus c q e squared t prime squared over this c to the fourth plus c squared p0 squared. Okay, good. Another substitution, and you've got it down. If you got it to your simple inverse hyperbolic sine. So what we get here, if I skip a couple lines, is y of t equals p0c over qe inverse, actually, let's write it this way, hyperbolic sine inverse of c q et divided by this energy expression, c to the fourth, c squared, p0 squared. So there's the time behavior as well. Now this one we can't just look at and see so well what's going on in terms of a limit as t goes to infinity. We're just seeing that it diverges. However, what we can finally do, we have x, yeah. So we have x up here in its complicated form. We can write y of x, or actually x of y. So to get x of y, we're going to solve for this numerator here, CQET, which we find right here. So we'll solve for that and square it and plug it in. Okay. So next, let's just say what we're trying to do here. Solve for, basically we're solving for t, but we're solving for the whole part there. And take into x of t, which is going to give us x as a function of y. Okay. Let's see, we have room on the board. We want to do some of this. Let's look right here. So here we've got y, so we have q e over p0c times y, and then we'll take the hyperbolic sign of that. Hyperbolic sign is equal to CQET divided by this thing in the denominator, m squared c to the fourth c squared p0 squared. So yeah, we multiply that over, and there is our time expression that we plug into that up there. Okay, now let's hold on to this x right here, since that's what we're working with. Okay. And we're squaring it, where are we? Right here. So we're squaring this thing, so that's the cross multiply, that's m squared c to the fourth is p naught squared plus hyperbolic sign squared. So this equals, we'll do right under here, so x of y is equal to 1 over QE square root of m squared c to the fourth plus c squared p0 squared. We can factor that out. 1 plus hyperbolic sign squared QEY over PLC. And in fact, let me go ahead and I'll write it in there. So 1 plus hyperbolic sign squared of the argument, QEY over POC. But that is the hyperbolic cosine squared, and we're going to pull it out of the square root. And then we'll have our final result. So I was going to skip that, but let's go ahead and keep that. So we have root m squared c to the fourth, c squared p0 squared, and then 1 plus hyperbolic sign squared is hyperbolic cosine squared, and we take the square root of that, we get hyperbolic cosine. So hyperbolic cosine of QEY over P0C. Good, so we're going to analyze that. So now we have the trajectory as a hyperbolic cosine, and you know, I set up x and y, so we're looking at something like this. I can substitute y and x and make it look more like what we're accustomed to. And in fact, I'll do that. So if we had x and y with E equals E times j hat, then we would have had, and I like working y of x better anyway, okay. Y of x would be equal to root m squared c to the fourth plus p0 c squared, and then the hyperbolic cosine of this whole thing, q e y over p0 c. Okay, so what we want to do, since this was a constant force problem, we want to look at the small velocity version of this. Right now we just have the trajectory, so if we want to look at the limiting case of small velocities, we have to go back into the meaning of these expressions right here. So first I'll make sure that I have the right, yeah. Good, so finally let's check the non-relativistic case, or the case where v is much less than c, velocity of our particle. Yeah, so hyperbolic cosine, okay, like that. Hyperbolic sine, goes like that. Okay. So let's have a look. In this case, we would have E0 is equal to mv0. Okay. And therefore, P0c squared is going to be much less than m squared c to the fourth. Okay. Because P0 squared is m squared v squared, much less than m squared c squared. Okay. So then we can just have m squared c to the fourth plus c squared. P0 squared goes to just mc squared. So we'll take it, we'll use that, and then the hyperbolic cosine of just say z is going to be equal to 1 plus, or I'll just write hyperbolic cosine of 0 plus hyperbolic cosine prime at 0 times z plus 1/2 double prime at 0 of z squared. So we expanded a Taylor series. That's a 1. The derivative of hyperbolic cosine is hyperbolic sine evaluated at 0 equals 0. So 1 plus 0 plus 1/2. Second derivative, that's the hyperbolic cosine double prime, which is back to hyperbolic cosine. Hyperbolic functions don't have the alternating signs plus and minus. They're always just plus, which is why, well, I erased it. Yeah, which is why this plus sine squared gives you cosine squared. Good, so second derivative, just a 1 times z squared. Good, so we can plug that in now. So v less than c, y is going to be going over to mc squared times 1 plus q e 1/2, 1 plus 1/2 QE. Now that P0 is MV0C squared y squared plus and so on. So what is that going to be? That's going to be equal to constant that we're going to ignore. We'll make a little room right here. Also, we're going to ignore plus 1/2. We got an MC squared, so we're going to cancel the M and we're going to get a C in the numerator. Actually, we're going to have one M in the denominator, we're going to cancel the C. So 1/2 QE squared over MV0 squared y squared. I missed a factor of QE. Ah yes, sorry. There's a factor of QE that I lost. QE Q times E, Q times E. That had to be because we had to get rid of that squared one there. And now we have to see, do we recognize this? Okay. So what we find is y is a constant plus 1/2 QE over MV0 squared y squared. Now if we compare that to projectile motion, so let's write compare to projectile motion, where we have y equals constant, say minus 1/2 g minus g x squared over 2 v0 squared. This would be the horizontal throw. The horizontal throw of something, you know, you launch it horizontally and it goes like that in X direction. And we don't have a minus sign here, but we could just by reversing the direction of the E field, so that's no big deal. QE over M, that would be F over M, which would be G. Okay. QE would be the force of the mass is acceleration is G. Okay. So yeah, we're good. And just to remind you guys, you know, if you go X equals V0t and Y equals, you know, H minus 1/2 GT squared, that's H minus 1/2 G, and then your T is, T squared is X squared over V0 squared. G is in the numerator, and that works out. Okay, good. So that is a fully tackled relativistic dynamics problem. Right, for us, the fundamental easiest one, or an easy one, 2 dimensions projectile motion. And we see there's a lot more going on there, but we have all the limiting cases. Okay, I'm going to consult the clock. running out of time. Okay, I have a few more things on our agenda. I should mention them now, because we're running out of hours. But this is a good okay. Okay, so here's what we have left. I want to do the Compton effect. Talk about the Compton effect, because what that is an inelastic collision, relativistic inelastic, a relativistic elastic collision. Elastic collision. And it has everything. Okay, we've already talked about, let's go ahead and set the Compton effect up. The Compton effect is where a high energy photon collides with an electron at rest and it scatters off of the electron. Okay. Now the photon is a relativistic particle with zero mass, but we have energy expressions for particles with zero mass. So yeah, let's go ahead and write this down. Actually, let me put here too, what else is on our list. We still want to talk about the Lorentz transformation and four vectors. In matrix form, which is a really good way to talk about four vectors, a way to introduce that. And I think we have enough time to do both. Okay. We'll start with the Compton effect right now. I'll set it up, and then we can take care of that and the Lorentz transformation. In terms of four vectors, what we want to do is take it back into our derivation of the relativistic dynamics that we've already done, and so that'll dovetail into that, and then we'll have a decent treatment. Okay, so I'll set up the Compton effect, and we'll complete the whole program in the last hour. First, now I'll just set up what all the ingredients are. So here we go, Compton effect. Let's get a big picture for starters. So we have a photon that's represented with a wavy line of energy E, original energy. This is all relativistic, and it collides with an electron, and we're going to have standard X and Y axes. It collides with the electron and scatters with an angle theta with respect to the horizontal. And now we have, actually this is E0, and this is the final energy of the photon. And then the electron goes off here as well with an angle phi. So yeah, I'm representing the photon, which is moving at the speed of light, with the wavy line, and the electron with the straight line. So we have, here I'll use a different color. So that's electron at rest. Mass m, and then it scatters eventually the photon scatters. So as far as this scattered electron goes, it has momentum and energy. The photon coming in and being scattered, each one also has momentum and energy. So there's energy and momentum. And momentum is conserved. And energy is conserved. So we just have to set up what momentum and energy are. And when we're all done doing momentum and energy conservation, we will use the quantum mechanical expression for the energy of the photon. Okay, but we're not there yet. But I'll put that down as the ingredient as well. Finally, we're going to have E equals H bar omega equals H nu equals HC divided by lambda, right? Lambda nu is equal to C, wavelength frequency. So that'll be the third ingredient. Okay. In terms of momentum, we just have the relativistic momentum expression, but we also have and we can write this as energy equals root m squared c to the fourth c squared p squared. We can have for the energy of a photon, and I'm using E. Okay. Right, we're not using it as a Hamiltonian, we're just using it as a magnitude here. So for the photon, it's just going to be C times P. P of the photon is just going to be E over C. So that's where the relativistic expression for the photon is going to come in. So let's start the momentum conservation and the energy conservation expressions. So we have momentum in Y, and that would be E over C sine of theta equals, equal and opposite down, P sub electron sine phi. And then X, we're going to have E0 over C is going to be equal to E over C cos theta plus E electron cos phi. I think I'll put the energy one up here as well. Energy is interesting. So the energy of the system initially is the energy of the photon, which is E0, and then the rest energy of the electron, which is mc squared. Okay. And then after the collision, right? You've got the energy of the scattered photon, and then the energy of the electron. So this is photon plus electron at rest. Photon plus electron that's moving is m squared c to the fourth plus c squared p electron squared. Okay, so those are the ingredients, these three equations, and we'll work with them next time. The goal is to get the Compton scattering formula, namely the wavelength of the scattered particle compared to the wavelength of the initial particle. That'll bring in this third equation as well. Okay, good. We'll continue this next time. See you then.